Alright, hey guys, what's going on today? We're going to be talking about complex manifolds a little bit more, and this time we're going to wrap up our discussion on holonomy, and then we're going to move into some more meaty mathematics on quantum gravity. So with that being said, let's get straight into the topic, and make sure to hit that like and subscribe button. Make sure to go into my Patreon page if you want to support the channel and get these notes, and if you want to see member-only content and early content, you can become a member on this YouTube channel as well. So without further ado, now let's get into the topic. So today we're going to be talking about complex manifolds and holonomy. We want to first talk about fiber bundles. So fiber bundles are a very, very important type of mathematical structure in physics, and we're just going to briefly touch upon them in this video, and then maybe in later videos we'll go deeper into them. I'm just going to provide a couple of examples because understanding fiber bundles is key to understanding quantum gravity, at least to some level. Okay, so we're going to start off by considering these three different types of manifolds: the E manifold, an M manifold, and an F manifold, and all of these are linked together in some way. Okay, the E manifold is called the bundle, the M manifold is called the base, and the F manifold is called the fiber. Okay. Now let's take some examples of this. And this will really help us solidify our understanding of what a bundle is. Really what a fiber bundle is a manifold embedded inside of another manifold. Okay? So we're going to take our base as being just the circle, S1 circle, and we're going to take our F manifold as just being the line, or the one-dimensional line of values going from -1 to 1. Okay, so our base manifold is the circle, and then we have our one-dimensional manifold radiating from the circle. This is why we call it sort of a fiber bundle. It looks like a fiber. You have these things attached to a base manifold. So the base manifold again is S1, and these lines are lines going from -1 to 1 and 0. So all the integers are going from -1 to 1. Okay, it doesn't necessarily have to be -1 to 1. It can be 2 to 1. It can be, or not 2 to 1. It can be 1 to 2. It can be 2 to 10. Whatever. The point is that we've defined a manifold F inside of another manifold M. Okay. The transition functions between the atlases on the base manifold M are just the identity, meaning that there's no twists or turns anywhere along the base. However, we can consider a Mobius strip. A Mobius strip is another example here. It's a similar structure, right? The base manifold is S1, and F is the fiber bundle, or the fiber, and but however, there's a difference. The difference here is that at one of the transition points, the transition function is z to -z. So there's a flip in the bundle. Okay. So, and that's what a Mobius strip is. Okay. If you're not aware of what a Mobius strip is really just it's a one-sided surface. It's a topologically interesting surface. Okay. It's a one-sided topologically interesting geometric object. Okay. And we're not going to go into Mobius strips here, just to say that this transition function is really what makes it unique. Okay. So there's some different categories of bundles. We're going to classify these bundles very briefly, just to really solidify our understanding of these. If F is a vector space, then we have a vector bundle. Okay. And an example of this is a tangent bundle. So in GR, in general relativity, we're talking about the entire collection of tangent spaces, all at the points along the manifold, right? So you have this base manifold that we've talked about, which is the four-dimensional manifold, and at every point you have a tangent space, and that tangent space is a vector space, and so we call this a vector bundle, specifically a tangent bundle. Okay. We can also consider the Lie groups, right? So Lie groups can be orthogonal to each other, therefore creating something of a vector space, but they're groups. They act on things. And so when they act on things, we have these matrices, right? So these U1, SU2, or SU3 gauge groups that can form their own sort of internal spaces on F or on the manifold. Internal spaces, I like to think of F as internal spaces, right? Because you have the base manifold, and then you have internal spaces at each point on the manifold. Okay? And we're going to really talk about this in quite depth when we start talking about triads, tetrads, and so forth. Okay? But the point here, again, is just that if it's a Lie group, in other words, a set of operators that obeys the Lie group, then we have a principal bundle. Okay? And so here's our base manifold M, and we can have vector spaces, or we can have a Lie group at each space. And so in one case we have a vector bundle, the other case we have a principal bundle. Okay, so now we want to talk about the transition functions. So we talked about the types of bundles. Let's talk about the transition functions. So non-trivial bundles occur when we need different transition functions to describe the space globally. Okay? We can therefore classify the bundles in three different types. The first type being topologically trivial bundles. Okay, so trivial bundles are the bundles where there's no, where the transition function is the same everywhere. Might be modified slightly a little bit, or it's the same everywhere, right? So, so we have the example here is just S1. S1 with no interesting topological structure to it, and it's got no curvature, and there's no flips like a Mobius strip would have or anything like that. So these bundles describe systems, as an example, with vanishing electromagnetic field strength. Okay. Then we have topologically trivial bundles. Again, the transition functions are smooth across the entire bundle. They're all the same. But in this case, the base manifold is curved. Okay. And we define curvature again through the connection, and we're going to see. Not through the connection, we define curvature through parallel transport, and so in that way. So in this case, we have a base manifold. It's curved, but the transition functions on this manifold again are not. It's smooth all over the place. They're all the same. Okay. And these bundles describe systems with non-vanishing electromagnetic field strength. So in one case, we had vanishing electromagnetic field strength. The other case, we have non-vanishing electromagnetic field strength. So the electromagnetic field strength, the curvature here actually causes the electromagnetic field strength to not go away. It's always going to be there at every point. Okay, so curvature has something to do with the non-vanishing strength of electromagnetism. We're not going to get into too much depth on that here. We're just going over fiber bundles before we go into any more depth later on. Then we have these type 3 bundles. We're not really going to talk about these that much either. These type 3 bundles are topologically non-trivial bundles. So again, non-triviality means that the transition function at some point along the bundle is different, right? It's not the same as everywhere else. And so we can take, for example, a base manifold of S1, and let's say at one of these overlaps on these two atlases, so we have the blue atlas and the red atlas, the transition function, say, is a Mobius strip transition function. It takes us from 1 to -1, okay? So there would be a flip right here, and that's a type 3 bundle. Now you can ask the question, what about if this is curved? You could classify that as a type 4 bundle, but as far as I know, that is something that has not been classified before. And the reason we're not going to talk about this that much is because they're not as common as far as I'm concerned, as far as I'm aware. And they describe systems with magnetic monopoles are present. So we're not going to get into magnetic monopoles. They're interesting objects, but that's a topic for advanced D&M, not for quantum gravity. To associate different fibers with different regions on the base space, we use projections, right? So a projection is going to take us from some space on one of the fibers, and it's going to it's going to project us down to the base. So we can call this projection. But then we have a section. Sections map different locations on the fibers. This is important when we start defining action principles, right? So this here is the section, right? So it's going to take us from some place on x mu, which is the curve, to some place up here. So this is the section. So we have projections and sections, and we just want to keep this in the forefront of our mind too. We'll come back to these topics later as well. In a tangent space, this is associated with mapping to a particular point on the tangent space. Okay. All right, so that is fiber bundles. Let's talk a little bit more about these transition functions now, because we're inching towards holonomy. That's the concept that we want to understand before we move on. So we can see that transition functions dictate the topology of the base space or the base manifold. In the case of the Mobius strip, we saw that in one neighborhood of the transition function flipped sign, changing the regular strip to the Mobius strip. The transition functions are analogous to connections on the manifold, right? So the idea here is that suppose you have a base manifold M, or suppose it's just a circle S1, and at one of the and you place two atlases on the manifold, and so you need to define a transition function on the overlap of the two atlases. And when you do that, you get that transition function is going to get you from one point to the next on the manifold. Well, what gets you from one point to the next when we're talking about GR? We're talking this thing. We're talking the Christoffel symbol, or the affine connection. Okay. So the affine connection is super important and is going to be a key player in quantum gravity, especially in loop quantum gravity, when we start talking about quantizing things. Okay, because the idea here is that we get we define regions so close to each other that we can, in theory, create an overlap between two things that are really arbitrarily close to each other. Can we quantize? Can we get so close to each other to the point where we can quantize? And what does the connection look like in that case? That's the question we want to ask ourselves. So in general relativity, this thing is the affine connection. In gauge field theory, it's these gauge fields. Okay. And we're not going to get too much into this right now, but we will later, okay? We can use these connections to define topologically invariant features as well on the fiber bundle. These features were proposed by Xingchen Chern, I think that's how you pronounce his name, as this thing, right? So we're not going to derive this. This isn't super important for right now. I'm just, again, wetting our feet with these concepts. This is an invariant feature. This is an invariant object of our entire fiber bundle E. And what it is, it's a determinant of this thing, where E recalls the entire bundle space, right? So the Ricci tensor, F is the Ricci tensor in the case of GR, or it can be the electromagnetic field tensor in the case of E&M, or some gauge field theory, okay? So this is why connections are so important, and this is one of the reasons why people in loop quantum gravity decided to look at connections as a fundamental object when addressing a gauge theory for general relativity. So now we're going to turn to the concept of holonomy. I keep wanting to say holonomy or something, but holonomy is what I used to say, but I think it's properly said holonomy. If I'm wrong, please correct me on that in the comments. But let's look at this now. So imagine all the possible paths that include some point on R2. Alright, so let's consider some of these paths. We're starting here at point P. Here's our point P. And we could take this path, we could take this path, we could take this weird path as well. The idea here is that if parallel transporting a vector along a path on any one of these paths results in nothing changing compared to the original vector. So I'll just erase this really quick. So we're traveling along, say, this path, and when we travel along this path, we're parallel transporting our vector, and when we do that, we get back to the original vector, right? So nothing really interesting happens in R2. What's interesting is what happens when we start considering topologically interesting spaces. So consider the sphere. So if we were to take a path, this path here, and we parallel transport, we don't get to the original vector, okay? And when we don't get to the original vector, we've rotated some angle. Now we can do this with another path, right? Another path, and we again don't get back to the original vector. Instead, we're perturbed by some angle. Say this is 140 degrees, say this is 160 degrees. Depending on the path, that'll give you the angle by which there's a perturbance or deviation. Okay, and the holonomy at this point P on the space is therefore a rotated vector. What generates these rotated vectors are matrices in the SO2 group. Okay, so the holonomy at point P on the sphere S2 is the SO2 rotation matrices, or the SO2 group. Okay, we can conceive of a set of matrices that represent this set of transformations, but fundamentally it's the SO2 group. Okay, but there's nothing special about the point P on the sphere because the sphere is symmetric all over the place, and so we have the holonomy or holonomy of S2 is SO2. Okay, so this leads us to an interesting rule. Okay, the holonomy of some manifold in real space, 2n, is SO2n. The number of generators that's involved in this group is 2n squared minus n. Okay. These Kahler manifolds. So if we recall when we were looking at complex geometry, we parsed out these two types of tangent spaces, right? So the holomorphic tangent space and the anti-holomorphic tangent space. And the idea here is that a Kahler manifold is going to stay in either the holomorphic or the anti-holomorphic. There's going to be no path that traverses the holomorphic and ends in the anti-holomorphic section and ends in the anti-holomorphic tangent space. So a Kahler manifold lands in the same tangent space, and it is of n, right? So we can because it's 2 times lower the dimension of r. Okay, because remember, complex number is a 1. It's represented as a vector, but it's a number, so it's a 1-dimensional. Whereas in R2, if you're taking R2, where you're looking at the x and y planes, right? So here, I'll just clarify that really quick. So in complex case, in the real case, complex number, you have just a real component and an imaginary component. Here you have a real and a real component. Okay, so we have 2 real dimensions. It's 2 real dimensions, and then here we have just 1 real dimension, so it's just 1 real dimension. Okay, so we have, and in this case the number of generators is n squared. And here this is our u transformations, or unitary transformations. Okay, so this is our Kahler manifolds. This is how we are going to define complex holonomy as opposed to real holonomy. And with that being said, this is, I hope you like this kind of content. Make sure to hit the like and subscribe button. Again, if you're interested in supporting the channel, you can go to my Patreon page. If you want to see videos early, you can, or get exclusive only content, then you can become a member as well on YouTube. So with that being said, I'll see you guys in the next video.